Good morning. So what we are going to see over on it, Abdina, the thing is to be that today what we are seeing output noise part, calculation of output noise part. So same thing we'll be seeing over on it. Output of the A to D converter is applied to a digital filter with the system function h of z is equivalent to 0.45 z divided by z minus 0.72. So we are in need to calculate the value of an output noise path of the digital filter when the input signal is quantized to 7 bits. So what it is given? P is equivalent to 7. Okay. So h of z into h of z inverse. So it is given as an h of z equivalent to 0.45 z divided by z minus 0.72. So z inverse now we have to make it of an 0.45 z inverse divided by z inverse minus 0.72. So that has to be multiplied with the value of an z inverse. What will happen? So 0.45 squared z power minus 1 divided by z minus 0.72 of 1 by z minus 0.72. Okay, so 0.45 squared is nothing but an 0.202 z power minus 1. So z minus 0.725, 1 minus, so take a cross multiplication, 1 minus 0.7 by z square. Okay, so after simplification, 0.2025 z inverse into z divided by z minus 0.72 into 1z minus 1 by 0.72. So when you are taking over here, so this will be equivalent to 0.28125 by z minus 0.72 of z minus 1.3889. So now the poles are at one thing to be 0.72 and the other thing to be 1.3889. So we know that surface integral of an 1 by 2 pi j surface integral of an h of z into h of z inverse into z inverse into dz. So we are in need to know the value of an residues. So the residues value is also given over here. Okay. So after simplifications, so we think is to be that the residues which lies in the poles are to be z minus 0.72. So replace z equivalent to 0.72. So one thing to be will be getting cancelled. So minus 0.28125 divided by 0.72 minus 1.3889. So finally, what will be getting the answer? 0.425 sigma squared E. So that we can is able to use the 2 power minus b by 12, where b is equivalent to 7 bits. Okay. So finally, you can able to write the answer. The next problem, consider the transfer function h of z is equivalent to h1 of z into h2 of z. h1 of z is equivalent to 1 by 1 minus a1 z inverse and h2 of z is equivalent to 1 by 1 minus a2 z inverse. So find the output round of noise part. Assume that is the value of an a1 is equivalent to 0.12 and a2 is equivalent to 0.6. Find the output round of noise part. So the round of noise part for model h of z is equivalent to h1 of z, h2 of z. So h1 can be replaced as an 1 by h of z is equivalent to 1 by 1 minus a1 z power minus 1 by 1 minus a2 z power minus 1. Let this equation to be 1. So whereas the noise transfer function by E2 of n is given as an H2 of z is equivalent to 1 by 1 minus A2 z power minus 1. Okay, the total steady state noise power, there is a round of noise power plus your round of noise power 2. So which is equivalent to 1 by 2 pi j surface integral of an h of z into h of z inverse into z inverse into dz. So 1 by 2 pi j surface integral of 1 by 1 minus a1 z power minus 1, 1 by 1 minus a2 z power minus 1, 1 by 1 minus a1 z power minus z power z and 1 by 1 minus a2 z into z minus 1 z. So the residues which are lying at 4 different values, one to be a1, another one to be a2, and another one to be 1 by a1, and another one to be at an 1 by a2. We know that if a1 and a2 are less than the poles, then it lies outside the unit circle. So the residues will also be equal to 0. So we'll have the corresponding poles only at z at a1 and a2. So we'll separate these two terms and we can able to get the final expression to be as an a1 divided by a1 minus a2, 1 minus a1 squared by into 1 by 1 minus a1 a2 plus a2 by a2 minus a1 into 1 by 1 minus a2 squared in 1 divided by 1 minus a1 into a2. So in the same way, similarly, if we proceeding for the next one, so we have to replace for z minus a2. So finally, what will be getting the expression 1 by 1 minus a2 square. Okay. So finally, we have to add both these values. So make an addition over on it. So it will be equivalent to 1 by 1 minus a2 squared plus a1 by a1 minus a2 into 1 by 1 minus a1 squared into 1 by 1 minus a1 a2 plus a2 by a2 minus a1 into 1 minus a2 squared plus 1 minus a2. Thus, after simplified all this expression, we have to replace a1 is equivalent to 0.5 and a2 is equivalent to 0.6. So substitute over on it. So finally, you'll be getting the expression 2 power minus 2b divided by 12 into of an 5.4315. Okay. The last thing is to be that we have to draw the quantization noise model for a second order system. H of z equivalent to 1 by 2 minus 1 minus 2 r cos theta inverse plus r squared z power minus 2, and we have to find out the steady state output noise variance. So H of z equivalent to 1 by 1 minus 2 r cos theta inverse plus r squared z power minus 2. So both the noise sources see the same transfer function. So the impulse functions, this is given by h of n is equivalent to r power n of sine of n plus 1 theta divided by sine theta into u of n. Now the steady state output noise variance is, so Norton squared plus Norton squared, but Norton squared is equivalent to Norton squared is equivalent to Norton squared summation is equal to minus infinity infinity h squared of n. So we'll be applying the value of h squared of n, sine squared of n plus 1 into theta divided by sine squared into theta. So substitute over on it. So r power 2 power n, r of 2 power n is equivalent to 1 minus cos 2 of n plus 1 theta, which is equivalent to cos 2 theta, which is equivalent to 1 minus 2 sine square theta. So substitute over here. So cos of 2 of n cos square theta, which is equivalent to e power j 2 of n square theta plus e power minus j 2 power n plus 1 theta. So e power j 2 theta divided by 1 minus r squared e power j 2 theta plus e power minus j 2 theta divided by 1 minus r squared e power minus j 2 theta. So which is given as an 1 by 1 minus r squared minus cos 2 theta minus r squared divided by 1 minus 2 r squared cos 2 theta plus r power 4. So we'll be getting over here 1 plus r squared 1 minus cos 2 theta, and then 1 minus r squared plus 1 plus 2 r cube cos 2 theta plus r power 4. So 1 plus r squared 2 power minus 2b by 6 divided by 1 minus r squared into 1 minus 2 r squared cos 2 theta plus r power 4. So this is the final answer for the given problem. The next one, we are in need to find out the coefficient quantization error. We know that IIR filter is characterized by system function h of z is equivalent to summation z is equal to 0 to m b z power minus b divided by 1 plus summation z is equivalent to 1 to n a z power minus b. So after quantizing, what will be getting over on it abdina, summation z is equal to 0 to m b z q z power minus b divided by 1 plus summation z is equivalent to 1 to n a power k q of z power minus b. So we can able to get that by the value of a and b. So a plus some del ab plus b plus del ab. So the quantization of filter coefficients alter the position of the poles and zeros in z plane. If the poles of desired filter lies close a unit circle, then the quantized filter poles may lie outside the unit circle, leading into instability of. So the thing is to be that, so deduction in poles and zeros also leads to deviation in frequency. So take on this question alone, the thing is to be that we have to consider an IIR filter at h of z is equivalent to 10 divided by 1 plus 0.5 z inverse, 1 minus 0.45 z inverse. Find the effect on quantization on pole location of the given system function in direct form and in cascade form. We have to take b is equivalent to 3 bits. Okay, so that we see in the next class. Thank you.